is really powerful.
Yes, it is. And we're going to look at a powerful method of solving linear nth order differential equations using what's called the annihilator approach. That means we wind up knocking stuff out. Okay, let's see. Here, written in operator notation, is our linear differential equation. And it's not homogeneous, you notice. But that means nth derivative applied to y. This is n minus first derivative applied to y. And if you look at this thing in a certain way, and we make L this linear differential operator, all this applied to y, then we can write the whole thing as linear operation applied to y equals g of x. And also note that any of these operators like this can be factored algebraically. D squared minus 5d plus 6 applied to y is d minus 3 times d minus 2 applied to y. So now we have something called an annihilator operator. Woo! Yes, okay, and this annihilator operator is going to help us with stuff, okay? Now, let's look at some annihilator operators. The nth differential operator annihilates 1, x, x squared, and all powers of x up to n minus 1. For instance, if you take a third derivative of x squared, you're going to get 0. So you've annihilated the x squared term. And as a matter of fact, it annihilates any linear combination of all powers of x less than this n. That's pretty easy to see. This one might be a little more of a challenge. D minus a to the n annihilates e to the ax, x times e to the ax, x squared times e to the ax, and up to x to the n minus 1 times e to the ax. Okay, we'll prove that in a little bit, but let me just demonstrate it for you for 1. Suppose n is 1, then d minus a eliminates e to the x, well, x to the 0 times e to the ax, so just e to the ax, because the derivative of e to the ax is a times e to the ax, and then when you subtract a times e to the ax, you get 0. So you've annihilated e to the ax with d minus a to the 1. And it also annihilates any linear combination of those, right? But that's pretty straightforward and not at all hard to believe. You're going to trust me on this one, that d squared minus constant 2a times d differential operator plus a squared plus b squared to the n annihilates all of these: e to the x cosine bx, e to the ax sine x bx, x times e to the ax cosine bx, x times e to the ax sine of bx, all the way up to x to the n minus 1 e to the ax cosine bx, and then here I put etc., but of course x to the n minus 1 e to the ax sine of bx is also annihilated by this differential operator. Now, I guess we'll prove one in the next section, in the next video.